Welcome to Chemistry Combustion Analysis. This presentation explores one of the most powerful techniques in analytical chemistry, the determination of elemental composition by burning a sample in excess oxygen. Used for over 2 centuries, combustion analysis remains the gold standard for finding the carbon, hydrogen, nitrogen, sulfur, and halogen content of organic compounds. We will travel from the historical origins of the method through the detailed apparatus of the combustion train to the mathematical framework that converts measured masses of carbon dioxide and water into precise empirical and molecular formulas. Along the way, you will learn how to perform the calculations step by step, discover how nitrogen and halogens are handled, and see the real-world applications in pharmaceuticals, polymers, and environmental science. 5 quiz questions will test your understanding, and 5 fully worked problems will drill the calculations. By the end, you will be able to take any combustion analysis data and determine the formula of the unknown compound. Here is the path we will follow through this presentation. We begin with the core concept, what combustion analysis is, and the fundamental chemistry behind it. A sample of known mass is burned in excess oxygen. All carbon converts to carbon dioxide, and all hydrogen converts to water. These gases are trapped in absorbents and weighed. Next, we examine the combustion train apparatus in detail, the furnace, the sample boat, the absorbent tubes, and how each component captures a specific combustion product. With the apparatus understood, we learn the calculations, how to convert the masses of carbon dioxide and water into masses of carbon and hydrogen, then into moles, and finally into the empirical formula. We then extend this to the molecular formula using the molar mass. Special cases round out the theory. Compounds containing nitrogen, sulfur, and halogens require modified absorbance and additional calculations. Finally, we present 5 quiz questions, 5 fully solved problems, and a comprehensive summary that ties every concept together. Combustion analysis is a quantitative analytical technique used to determine the elemental composition of an organic compound. A precisely weighed sample is completely burned in a stream of pure oxygen gas at high temperature, typically between 950 and 1000 degrees Celsius. Under these conditions, every carbon atom in the sample is converted to carbon dioxide gas, every hydrogen atom is converted to water vapor, and any nitrogen present is converted to nitrogen gas or nitrogen oxides. The combustion products are carried by the oxygen stream through a series of chemical traps, called absorbents, that selectively capture each product. The increase in mass of each absorbent tells us exactly how much carbon dioxide and water were produced. From these masses, we calculate backward to find the masses of carbon and hydrogen that were originally present in the sample. If the compound contains only carbon, hydrogen, and oxygen, the mass of oxygen is found by subtracting the masses of carbon and hydrogen from the original sample mass. This technique was pioneered by Joseph Louis Proust in the late 18th century and perfected by Justus von Liebig in the 1830s, and it remains one of the most reliable methods for determining empirical formulas. The combustion train is the sequence of apparatus through which the sample and its combustion products travel. At the front is a quartz combustion tube inside a furnace heated to 950 degrees Celsius. The sample, weighed to the nearest 0.1 milligram, is placed in a platinum or ceramic boat and pushed into the hot zone. A steady stream of pure oxygen flows through the tube, ensuring complete combustion. As the gases leave the furnace, they first encounter a tube packed with anhydrous magnesium perchlorate, a powerful drying agent that absorbs all water vapor. The increase in mass of this tube gives the mass of water produced. Next, the dry gases pass through a tube packed with ascarite, sodium hydroxide on an inert support, which absorbs carbon dioxide by forming sodium carbonate. The increase in mass of this tube gives the mass of carbon dioxide produced. If the compound contains nitrogen, a final section packed with copper metal reduces any nitrogen oxides to nitrogen gas. For sulfur analysis, the sulfur trioxide produced is absorbed on zinc oxide. Halogens are captured on a silver wool plug, forming silver halides. The entire train is a masterpiece of selective chemical trapping. Let us understand exactly what happens at the molecular level when an organic compound burns in excess oxygen. The general combustion reaction for a hydrocarbon is CXHY plus oxygen yields XCO2 plus Y over 2H2O. For example, methane burns as CH4 plus 2O2 yields CO2 plus 2H2O. For a compound containing oxygen, the general equation includes the oxygen from the compound itself. The key insight is that all carbon atoms are quantitatively converted to carbon dioxide molecules, and all hydrogen atoms are quantitatively converted to water molecules. Each H2 molecule contains exactly one carbon atom, and each H2O molecule contains exactly two hydrogen atoms. This is what makes the calculation possible. The stoichiometry is 1-to-1 between carbon atoms and CO2 molecules, and 2-to-1 between hydrogen atoms and H2O molecules. The molar masses connect the measured masses. 1 mole of CO2, 44.01 grams, contains 12.01 grams of carbon. 1 mole of H2O, 18.016 grams, contains 2.016 grams of hydrogen. These ratios are the foundation of every combustion analysis calculation. Now we arrive at the core calculation of combustion analysis. Given the masses of CO2 and H2O produced from burning a known mass of sample, we calculate the masses of carbon and hydrogen. The fraction of carbon in CO2 is the molar mass of carbon divided by the molar mass of CO2, which is 12.01 divided by 44.01, or 0.2729. So the mass of carbon equals the mass of CO2 times 0.2729. Similarly, the fraction of hydrogen in H2O is 2.016 divided by 18.016, or 0.119. So the mass of hydrogen equals the mass of H2O times 0.119. For example, a sample produces 0.880 grams of COW and 0.360 grams of H2O. The mass of carbon is 0.880 times 0.2729, which equals 0.240 grams. The mass of hydrogen is 0.360 times 0.119, which equals 0.0403 grams. If oxygen is also present, we subtract the masses of carbon and hydrogen from the original sample mass to find the mass of oxygen. This three-step process of calculating masses of individual elements from the combustion products is the heart of the method. Once we know the mass of each element in the sample, we can determine the empirical formula, the simplest whole number ratio of atoms in the compound. The process has 4 steps. Step 1. Convert each element's mass to moles by dividing by its molar mass. Step 2. Identify the smallest number of moles among all the elements. Step 3. Divide every element's mole value by this smallest number. Step 4. If the resulting ratios are not whole numbers, multiply all of them by the smallest integer that makes every ratio a whole number. For example, a 0.200 gram sample of a compound containing carbon, hydrogen, and oxygen produces 0.440 grams of CO2 and 0.180 grams of H2O. The mass of carbon is 0.440 times 0.2729, which equals 0.120 grams. The mass of hydrogen is 0.180 times 0.119, which equals 0.0201 grams. The mass of oxygen is 0.200 minus 0.120 minus 0.0201, which equals 0.0599 grams. Converting to moles, carbon is 0.0100, hydrogen is 0.0199, and oxygen is 0.00374. The smallest value is 0.00374. Dividing gives us the ratio needed to determine the empirical formula. The empirical formula gives the simplest whole number ratio of atoms, but it does not tell us the actual number of atoms in a molecule. For that, we need the molecular formula. The molecular formula is always a whole number multiple of the empirical formula. To find the multiplier N, we divide the molar mass of the compound by the empirical formula mass. The empirical formula mass is simply the sum of the atomic masses of all atoms in the empirical formula. For example, the empirical formula CH2O has an empirical formula mass of 12.01 plus 2.016 plus 16.00, which equals 30.03 grams per mole. If the experimentally determined molar mass of the compound is 180.16 grams per mole, then N equals 180.16 divided by 30.03, which equals 6. So the molecular formula is C6H_12O6, which is the formula of glucose. Multiple compounds can share the same empirical formula. For example, both glucose and acetic acid have the same empirical formula CH_2O. This is why the molar mass is essential. Without it, we can only narrow down the possibilities to the empirical formula. Combustion analysis becomes more complex when the sample contains elements beyond carbon, hydrogen, and oxygen. For nitrogen-containing compounds, the combustion products include nitrogen gas and nitrogen oxides. A special section of the combustion train packed with copper metal at 600 degrees Celsius reduces all nitrogen oxides back to N-2 gas. The nitrogen gas is then measured by a thermal conductivity detector or by collecting it over a potassium hydroxide solution. For sulfur-containing compounds, sulfur burns to sulfur trioxide, which is absorbed on zinc oxide or a silica gel column forming sulfuric acid. The mass of sulfate is then determined gravimetrically. For halogen-containing compounds, including chlorine, bromine, and iodine, the combustion products are passed over a silver wool plug heated to around 500 degrees Celsius. The halogen reacts with silver to form silver halide, which is weighed. For fluorine, a calcium oxide absorber is used to form calcium fluoride. These modified procedures make combustion analysis applicable to virtually any organic compound. Combustion analysis is far from a historical curiosity. It remains a vital tool in modern chemistry. In the pharmaceutical industry, every new drug candidate must have its elemental composition verified by combustion analysis as part of quality control. A purity of 99.5% or higher is typically required. In polymer chemistry, combustion analysis determines the monomer composition and degree of cross-linking in plastic materials. In environmental science, the carbon-to-nitrogen ratio of soil samples is routinely measured to assess soil health and decomposition rates. In the food industry, the protein content of foods is estimated from the nitrogen content determined by combustion analysis. Modern automated elemental analyzers, such as the CHNS analyzer, can process a sample in under 10 minutes and report the percentages of carbon, hydrogen, nitrogen, sulfur, and oxygen simultaneously. These instruments are used in thousands of laboratories worldwide, from academic research to industrial quality control. Quiz question 1. A 0.150 gram sample produces 0.220 grams of CO done for SO2. What is the mass of carbon? Option A, 0.040 grams. Option B, 0.060 grams. Option C, 0.080 grams. Option D, 0.100 grams. Take a moment to calculate your answer. Quiz question 2. A compound is 40% carbon, 6.67% hydrogen, and 53.33% oxygen by mass. What is its empirical formula? Option A, CH2O. Option B, C_4O2. Option C, C_6O3. Option D, CHO. Take a moment to calculate your answer. Quiz question 3. Which substance is used to absorb water in a combustion train? Option A, NaOH or ascarite. Option B, magnesium perchlorate. Option C, copper oxide. Option D, calcium hydroxide. Take a moment to think. Quiz question 4. The empirical formula of a compound is CH2, and its molar mass is 42 grams per mole. What is the molecular formula? Option A, CH2. Option B, C_2H_. Option C, C_6. Option D, C_4H_8. Take a moment to calculate your answer. Quiz question 5. Combustion of 0.2 thousand grams of a hydrocarbon gives 0.586 grams of CO2. What is the percentage of carbon in the compound? Option A, 40%. Option B, 60%. Option C, 80%. Option D, 90%. Take a moment to calculate your answer. Problem 1. Finding the empirical formula. A 0.150 gram sample of an organic compound containing carbon, hydrogen, and oxygen produces 0.220 grams of CO2 and 0.090 grams of H2O. Step 1. Calculate the mass of carbon. Mass of carbon equals 0.220 times 12.01 divided by 44.01, which equals 0.060 grams. Step 2. Calculate the mass of hydrogen. Mass of hydrogen equals 0.090 times 2.016 divided by 18.016, which equals 0.010 grams. Then find the mass of oxygen by subtraction. 0.150 minus 0.060 minus 0.010 equals 0.080 grams. Step 3. Convert each mass to moles. Carbon, 0.0050 moles. Hydrogen, 0.010 moles. Oxygen, 0.0050 moles. Step 4. Divide by the smallest value, 0.0050. The ratio is 1 to 2 to 1. The empirical formula is CH2O. Problem 2. Finding the molecular formula. A compound has the empirical formula CH2O and a molar mass of 180 grams per mole. Find the molecular formula. Step 1. Calculate the empirical formula mass. The empirical formula mass of CH2O is 12.01 plus 2.016 plus 16.00, which equals 30.03 grams per mole. Step 2. Divide the molecular mass by the empirical formula mass. 180 divided by 30.03 equals 6. Step 3. Multiply the empirical formula by N equals 6. The molecular formula is C6H12O6. This is the formula of glucose, a simple sugar that is fundamental to life. Notice that the empirical formula mass divided perfectly into the molecular mass, confirming the result. Problem 3. Hydrocarbon analysis. A 0.250 gram sample of a hydrocarbon containing only carbon and hydrogen produces 0.850 grams of CO2 and 0.174 grams of H2O. The molar mass is 78 grams per mole. Find the molecular formula. Step 1. Calculate the masses. Mass of carbon is 0.850 times 12 divided by 44 equals 0.232 grams. Mass of hydrogen is 0.174 times 2 divided by 18 equals 0.0193 grams. Notice that the sum of carbon and hydrogen masses very nearly equals the sample mass, confirming only these two elements are present. Step 2. Convert to moles. Carbon, 0.232 divided by 12 equals 0.0193 moles. Hydrogen, 0.0193 divided by 1 equals 0.0193 moles. The ratio is approximately 1 to 1. The empirical formula is CH. Step 3. The empirical formula mass is 13 grams per mole. N equals 78 divided by 13, which equals 6. The molecular formula is C6H6, which is benzene. Problem 4. Analysis with nitrogen. A 0.300 gram sample containing carbon, hydrogen, and nitrogen produces 0.660 grams of CO2 and 0.135 grams of H2O. Find the percentage composition and empirical formula. Step 1. Find the masses. Mass of carbon is 0.660 times 12 divided by 44, which equals 0.180 grams. The percentage of carbon is 0.180 divided by 0.300 times 100%, which equals 60%. Mass of hydrogen is 0.135 times 2 divided by 18, which equals 0.015 grams. The percentage of hydrogen is 0.015 divided by 0.300 times 100%, which equals 5%. Mass of nitrogen is found by subtraction, 0.300 minus 0.180 minus 0.015 equals 0.105 grams. The percentage of nitrogen is 0.105 divided by 0.300 times 100%, which equals 35%. Step 2. Convert to moles. Carbon, 0.0150 moles. Hydrogen, 0.0150 moles. Nitrogen, 0.0075 moles. Step 3. Divide by the smallest, 0.0075. The ratio is 2 to 2 to 1. The empirical formula is C2H due to N. Problem 5. Oxygen-containing compound. A 0.200 gram sample containing carbon, hydrogen, and oxygen produces 0.293 grams of CO2 and 0.120 grams of H2O. The molar mass is 60 grams per mole. Find the molecular formula. Step 1. Calculate the masses. Mass of carbon is 0.293 times 12 divided by 44, which equals 0.080 grams. Mass of hydrogen is 0.120 times 2 divided by 18, which equals 0.0133 grams. Mass of oxygen is 0.200 minus 0.080 minus 0.0133, which equals 0.1067 grams. Step 2. Convert to moles. Carbon, 0.00667 moles. Hydrogen, 0.0133 moles. Oxygen, 0.00667 moles. The ratio is 1 to 2 to 1. The empirical formula is CH2O with mass 30. Step 3. N equals 60 divided by 30, which equals 2. The molecular formula is C2H_4O2, which is acetic acid. Let us bring everything together in a comprehensive review. Combustion analysis rests on 5 foundational concepts. First, the fundamental chemistry. Every carbon atom in a sample becomes one CO2 molecule, and every two hydrogen atoms become one H2O molecule. The ratios 12.01 over 44.01 for carbon and 2.016 over 18.016 for hydrogen are the mathematical keys. Second, the combustion train, a furnace at 950 degrees Celsius, magnesium perchlorate to absorb water, and a scarite to absorb CO2. Third, the calculation sequence. From masses of CO2 and H2O, find masses of carbon and hydrogen, convert to moles, and divide by the smallest to get the empirical formula. Fourth, the molecular formula. Divide the molar mass by the empirical formula mass. Fifth, special cases. Nitrogen needs copper. Sulfur uses zinc oxide. Halogens use silver wool. With these tools, you can determine the elemental composition of almost any organic compound. Thank you for learning with